You are standing on roughly 6 septillion kilograms of rock and iron. Finding that exact number seems like a job for a multi-billion-dollar space agency, but you can calculate the exact mass of the Earth yourself, right at home, using fishing line, some water jugs, and a laser pointer. In 1798, Henry Cavendish used a torsion balance, designed by John Michell, to measure the faint gravitational pull between lead spheres. To weigh the world, he needed two numbers: Earth's local downward pull, lowercase g, and the universal gravitational constant, uppercase g. Over the next few minutes, we are going to walk through how to build your own highly sensitive physics lab. Step by step, we will gather the data you need to calculate a number with 24 zeros. Understanding gravity is possible outside of elite observatories. It is a universal force that can be decoded from anyone's backyard. Step 1 is pinning down lowercase g. For this, you need to build a simple pendulum. Tie a heavy weight, like a steel nut, to a piece of string. Measure the exact length of that string from the pivot point at the top down to the center of the nut. Pull the nut back and let it go. Start a stopwatch and time exactly 10 full back and forth swings. By dividing that total time by 10, you find the period of a single swing, represented by the variable t. Doing 10 swings averages out the delay of your thumb hitting the stopwatch button. This animation shows one crucial rule for this step: keep your starting angle tight. If you pull the pendulum back more than 15 degrees, the math breaks down. Relying on the small angle approximation, the swing must stay close to the center line. To find g, we multiply 4 times pi squared times your string's length, divided by the period squared. Run those numbers to get roughly 9.8 meters per second squared. With a piece of string and a stopwatch, you have successfully measured the local downward pull of the Earth. Half of our cosmic equation is complete. This image shows our goal for step 2, which is much harder. We need to measure uppercase g, the universal gravitational constant. To do this, we build a torsion balance. Suspend a stable horizontal wooden rod from the ceiling using a thin fiber, like high-quality fishing line. At each end of that rod, attach a small weight, like a lead fishing sinker. Then, at the exact center where the string meets the rod, carefully glue a small mirror. Gravity is the weakest of the 4 fundamental forces. A tiny magnet can lift a paperclip against the gravitational pull of the entire planet. So to see 2 small weights pull on each other, your fishing line must be incredibly sensitive to the slightest twisting motion. Step 3 is isolation. Because this force is so faint, a slight draft or the heat rising off your own body will ruin the data. Eliminate this interference by enclosing the whole setup inside a styrofoam or cardboard box, leaving only a tiny window to see the mirror. Locking away the apparatus protects it from the surrounding environment. Without that physical barrier, the ambient noise of a normal room completely buries the pure signal of gravity. Professional astrophysicists battle the same background noise that plagues a backyard garage. As this 3D Earth geoid model shows, variations in crust thickness, shifting groundwater, and even the changing seasons create massive gravitational interference on a planetary scale. Spacecraft like the GRACE follow-on mission orbit the Earth to map out these density fluctuations. But even in low Earth orbit, the mass of moving livestock or ocean tides below can skew attempts to measure the absolute value of g. To get a truly flawless measurement of the gravitational constant, researchers have proposed sending a probe deep into space, well past the asteroid belt and the orbit of Jupiter, completely free from the gravitational pull of comets and planetary masses. Fortunately, you can work around the noise in your garage using step 4, the optical lever. Shine a laser pointer through the window of your isolation box so it hits the mirror. The beam will bounce off and hit a ruler taped to a distant wall. Now, place 2 5-gallon water jugs just outside the box, positioned near your suspended lead sinkers. These heavy jugs are your massive gravitational attractors. Inside the box, the mass of the water jugs begins pulling on the lead sinkers. As they slowly attract each other, the horizontal rod rotates, the fishing line twists, and as the mirror turns, that laser dot creeps millimeter by millimeter across your ruler. Because the ruler is far away, the tiny rotation is magnified. Tracking exactly how far that dot travels, gives you the angle of deflection, which provides the math required to calculate uppercase G. Step 5 is bringing the puzzle pieces together. You have your local gravity value and you have your universal gravitational constant. You just need one known geographic fact, the radius of the Earth, which is roughly 6,378 kilometers. This diagram shows how we bring all the data together. We take the standard equation for the weight of an object and rearrange it to solve for the mass of the planet. The formula becomes Earth's mass equals lowercase g times the radius squared divided by big G. Plug in the numbers from your pendulum and laser pointer. The result resolves to 5.97 times 10 to the 24th power kilograms. That is 5,970,970,970,970,970 quadrillion kilograms. You took basic arithmetic, a swinging piece of metal, and some twisted string, and used them to accurately calculate the mass of the planet beneath your feet. We started by timing a steel nut swinging on a string, and finished by recreating a 225-year-old experiment to weigh the world. By carefully isolating your setup and tracking the optical lever, you succeeded by overcoming the exact same environmental noise hurdles that challenge professional astrophysicists today. Now you can test the variables yourself. Try swapping the fishing line for a thin copper wire to see how the torsion changes. Or run the pendulum experiment at the top of a mountain versus sea level to calculate how local gravity shifts with altitude. The fundamental laws of nature are not hidden away in a textbook. They are actively happening all around us, accessible to anyone willing to look closely enough. Subscribe for more ways to decode the universe from your own backyard.